Good morning, everyone. I think again this I can start class now. Okay. The first thing I want to let you know is you will have some online homework this week. Okay. 5.1, 5.2, 5.3. We will not have the online homework here. The online homework is 7.1, 7.2, 7.3. We will know interactive review this week. We will not have interactive review. Okay. And we will have the online homework will be on Sunday, this Sunday. And we also have the heading homework 5. Cannot be on Sunday. The heading homework 5 will be on March 20. Okay, that's all the things about the online homework. Okay, and you see here is 8.1, 8.4 is due before I don't know, after spring break. Okay, after 1 week spring break. We don't need to do this. Okay. Any questions so far about the assignment? Okay. So that's all the things about the assignment this week. Okay, and now we will move on to the next chapter. Chapter 7 is the central limit theorem. In this course, we will not. I just give you an introduction about the central limit theorem. I'm not through this because to prove the central limit theorem, we have to have the knowledge about the calculus. And you will know how to prove this theorem in the higher course, maybe in master course about statistics, about probability. Okay. So now we just introduction about this. Okay. Okay. Now I will, and the goal of today is use the central limit theorem to identify the characteristic of the sampling distribution when we know information about the population. For example, I will recall something about population and sample. Okay, for example, you have the population. Okay, the population may be. I give you an example at the beginning in this semester. For example, student at West State University is a population. Or the professor at West State University is a population, okay? And the subset of this of the population will be called a sample, right? Okay. Subset will be called a sample. Okay. For example, when I talk about a population, like the population is a student at West State University, right? And a sample is the student, for example, a student in my class, okay? Is a subset of the population, right? That is a sample. Okay. And now, if we know information about population, for example, we know about the mean, we know about the deviation, we know about something like this. And the question is, how do we know about this? Okay. What is the relationship between the sample means and the means of the population, something like this? What about the deviation of sample and the population, something like this? Okay, so today we will solve this. We will solve this problem. We will know, if we know the information about population, we will know the characteristic of the sample. Okay, that's either the goal of this chapter. Okay, clear, right? Okay, that is just the introduction about this. Okay, so now, okay, we will move on to the first definitions. That's called the sampling distribution. Okay, I will give you the example about the population. For example, I have the population is student at Wednesday University. When I consider the population like this, okay, here we have the population is student at Wednesday University, and you know that when I choose one subset of the population, for example, I will choose the student in my class, something like this. That is a sample, right? Okay. Or I choose student in my college class. Okay. In my college class. Okay. Well, in A. Okay. Professor, something like this. And I choose student in another one. In the class B something. And I choose okay. And for each sample, you will have the, for example, I want to measure the average score of average GPA, okay, average GPA of student, okay, for example, like this, okay, and I will investigate the average GPA of student in my class, and they will give me the average H bar, okay, H1. Okay, H1 is the average GPA of student in my class, for example. And H2 bar will be the average GPA of student in the class of Professor A, something like this. And we have H bar here is the GPA, average GPA of student in class A, something like this. Okay. And you see, you will know that H1, H2, and H3 will be different, right? Because the score in each class will be different, right? Okay. And the population or the distribution of H1, H2, and H3 is called the sampling distribution. Okay. When we measure all the sample here, or each sample here, we will have the table for this, or we have the graph for this, and this is called the sampling distribution. Okay. That is definition. The sampling distribution is the distribution of the values of a particular sample statistic for all possible samples. Okay. Here we have the numerical distribution is the average GPA of student. So to find the sampling distribution, we will measure all the GPA students of each sample. Okay. And after that we will draw the graph of this. And this graph will be the sampling distribution of the average GPA student at Wednesday University. Okay? Clear, right? Okay, that is the definition of sampling distribution. Okay. And the second definition here is the sampling distribution of sample means. Okay, that's sample means. Okay. This is a special case of sampling distribution. Okay. The sampling distribution of sample mean, that is the distribution of the sample mean for all possible samples. For example, here we have H1 bar is average GPA. In this case, H bar 1 is also the mean of this sample, right? And H bar here is also the sample mean of this sample. Something like this. And we will summarize all the means, and after that we will draw the picture for this, and this is called the sampling distribution of sample means. Okay, that's the things. And the question here is, what is the relationship between the sampling distribution of sample means and the means of population? Okay, if we have the mean of population mu here, so how do we know the mean of the sampling distribution? Okay, how do we measure the mean of the sampling distribution? Okay, so that in this case we need to use the central limit theorem. The central limit theorem will answer this question. Okay. Okay, I will give you an example. It's similar like this. Okay, in this case, I will consider the population, either the last time of fish. That means all the fish in the tank, right? That's in the population. And you see that I want to choose the sample mean of 50 fish. Okay. Okay, I take separate. Okay, I will take separate fish. Okay, 50 fish, and I will measure its mean in H1. Okay, and another one will be H2, and you know that H1 will not be equal to H2, right? And now I will taking 1,000 sample like this, and after that I will draw a picture about the sample, and that's either the sampling distribution. That is just a sample example about the sampling distribution. Okay, you can understand the sample distribution by this example here, or you can look at the example I provided here. Okay, so now I will go to the theorem about the central limit theorem. The central limit theorem will state three things. Okay. The first one, when we talk about the central limit theorem, we need to look at the assumption. What is the assumption? When we can apply the central limit theorem? When we can apply this? Okay. When we the condition to apply the central limit theorem is the sample size. Okay. The sample size is at least 30. Okay, is at least 30. Or the population is normal distribution. We need to it needs to be satisfied one of these two conditions. Okay, if the population is not satisfied this condition, you cannot apply the central limit theorem, right? Okay, that's either the assumption. We have two assumptions here. The sample size should be greater than or equal to 30, okay, at least. Or the population, the distribution of population is well shaped. We have two conditions. Okay. If the data or the population doesn't satisfy these conditions, so we cannot apply the central limit theorem. Okay, that is the assumption. What about the conclusion? We have three conclusions. Okay, the first one, they will talk about the mean of sampling distribution. What is the mean of sampling distribution? Okay, and they say that the mean of sampling distribution equals to the mean of population. Okay, so if you know the mean of population, you can say that the mean of sampling distribution is equal. Okay, it's like that. The first one, the mean of the sampling distribution will be equal to the mean of the population. Okay. This is the mean of the sampling distribution. So be equal to the mean of the population. Okay, that is the first relationship between the mean of population and mean of sampling distribution. Okay, maybe it's right. The formula is not clear, but when you look at in your computers, it might be it's more clear. Okay, it's be clearer. Okay, I write down here for you to see. Okay, the second statement, we talk about the standard deviation, the standard deviation of the sampling distribution and the population. Okay, if we know the standard deviation of the okay, I will write down here the sigma here is the maybe it's not easy to look. Okay. If I have the sigma is the standard deviation of the population, something like this. If I have the sigma here is the standard deviation of the population. So what about the standard deviation of sampling distribution? Okay, it's not equal. It's not equal. And in this case, the deviation of sampling distribution will be equal to the standard deviation over to square root of n. Okay, this is the formula, and this is the relationship between the standard deviation of the population and the standard deviation of sampling distribution. Okay, that is the second statement. Okay. When we know about the mean, when we know about the standard deviation, we will know the characteristic of the sample, right? And the third statement, we talk about the shape of the sampling distribution. The shape of sampling distribution will be approach the normal distribution, regardless the shape of population. Okay, maybe in this case, the shape of the population will be skewed to the right, skewed to the left, something like this. But the shape of sampling distribution will be approach the normal distribution. Okay. When we choose the larger size, for example, we choose the sample size is 1,000, 10,000, 1 million, something like that. The better normal distribution approximation will be. Okay. That is the statement of central limit theorem. So now I will give you the example for this to apply the central limit theorem. Okay? And you look at the screen. Suppose that the standard deviation of movie ticket prices in the United States is 0.72. Okay. Suppose sample means are calculated for sample of size 52. Okay. So the question here is, what would be the standard deviation of the sampling distribution? Okay, so now you will look at the keyword here. The keyword here is ask you to find the standard deviation of the sampling distribution, right? Okay, they ask you to find the standard deviation. That means they ask you to find the sigma x bar, right? Okay, they ask you to find this. And now we will apply this formula. Okay, could you tell me what is n in this case? What is n in this case? N here is the sample size. What is n in this case? Robin, please.
Is it 52?
Yeah, exactly. Thank you. The sample size in this case is 52. So in this case, n is 52, right? Clear, right? Okay. And now they ask you to find the standard deviation of sampling distribution. That means they ask you to find the sigma x bar, right? And you know that sigma x bar should be calculated by sigma over square root of n, right? And sigma here is the standard deviation of population. What about sigma in this case? What about sigma in this case? What about, okay. Okay.
72 cents.
Huh?
The standard deviation is 72 cents.
Yeah, exactly. What's your name, please?
Shreya.
Sia. Okay, sorry.
Shreya.
Sia, okay, Sia. Sia, okay. Okay, in this case, the standard deviation is 0.72, okay? And the square root of n is square root of 32, okay? And you will use calculator, okay? Use calculator to calculate this. This value should be, okay, 0.09985, something like that. Sometimes they will round it is just 0.1. It's the same. 0.1. if you want to route it to one decimal places, okay, it's just 0 or 1. Clear, right? And that is the applies we apply the central limit theorem to calculate the standard deviation of sampling distribution. Okay. Okay, we will move on to the next example. Okay, and the following histogram represents the population distribution of the weights of 600 horse jockeys. The mean of the population is 1,016.2 pounds, and the standard deviation is 3.9 pounds. Okay, that is the question. And the question here is, let's now consider the sampling distribution of the sample mean for sample size is n is 45. Okay, the question A is, can the central limit theorem can be applied to this sampling distribution? Okay, so could you tell me, can the central limit theorem be applied to this sampling distribution? Okay, you please.
Yes, because the sample size is greater than 30.
Okay, what's your name, please?
Alondra.
Alondra, thank you. Exactly, because when we want to apply the central limit theorem, we have to satisfy one of two conditions. The first one, the sample size will be at least 30, right? 30. And here, 45 is greater than 30, so it's 35, right? Okay, and now we can apply the central limit theorem. Okay, question A finished. About puppy, what is the sampling distribution mean? Okay, they ask you to find the sampling distribution mean. That means they ask you to find mu x bar, right? Mu x bar. Okay, look at the keyword here, the sampling distribution mean. They ask you to find the mu x bar. And you know that when the central limit theorem say that the mu x bar should be equal to mu, right? Should be equal to mu. So you can look at the statement 1. The mean of sampling distribution of the sample mean equal to the mean of population, right? And now you will have this formula, right? And now the thing here is we need to find what is the mean of population, and you will look at the example. Okay, in this case, could you tell me what is the mean of population? What is the mean of population? Delaney, right?
Yeah. 116.2.
Yeah, exactly. Exactly. Okay, so you look at the keyword here, the mean of population is 16.2. So that will finish copy. Okay, clear, right? Okay. About box C, what is the sampling distribution standard deviation? Okay. So now the keyword here, the sampling distribution standard deviation. Okay. That means we need to find the sigma x bar. Okay. And the central limit theorem say that the standard deviation of sampling distribution will be equal to the standard deviation of the population over square root of n. Okay. And now, could you tell me what is sigma and what is n in this case? Lead, please.
Sigma is 3.9 and n is 45.
Okay. 3.9. Okay, and okay. Thank you. Exactly. 3.9 and the n here is 0.5. And now you will get the result is, I will use the calculator, and the result should be 0.58. Okay, that is the standard deviation, okay, of the sample mean. Okay. And what is the sampling distribution shape? Okay. In this case, we can use the central limit theorem. which is a statement in this case. We have three statements in the central limit theorem, right? The first one, we talk about the mean. The second one, we talk about the standard deviation. And the third statement, we talk about the shape, okay? So in this case, we can apply the central limit theorem, and we apply the statement 3 of the central limit theorem, right? And statement 3 say that the sampling distribution shape of the sampling distribution is the bell shape, right? Normal distribution. Okay? And we can look down. It's in the bell shape distribution because of the central limit theorem, right? Okay. Any questions so far about this? Okay. Okay, now we will move on to the next example. Applying the central limit theorem. The following graph displays the starting salaries for law school graduates entering the workforce in 2007. Right? Okay, so back to question. Consider the sampling distribution of the sample means created from this population for sample of size 25. Can the central limit theorem be applied in this situation? Okay, Delaney, please.
No,
Why?
because the size has to be, is it 30 and above or just above 30?
Yeah, exactly. Okay, but we forget one thing. It doesn't satisfy the sample size, but we need to check the population is normal distribution or not. Okay, in this case, both conditions are not satisfied, right? This population is not bell-shaped distribution, right? Okay, so both of them are not satisfied. It's the sample size is not greater than 30, and the population is not the bell-shaped distribution. In this case, both conditions are not satisfied, and we cannot use the central limit theorem, right? Okay, thank you, Delaney. Okay, but be careful when we explain about the reason. Okay, the reason here is both conditions are not satisfied, not just one condition, right? Okay, in this case, the central limit theorem cannot be applied. Okay, and what about B? Consider the sampling distribution of the sample mean created from this population for sample size of 50. Can the central limit theorem can be applied for this exact situation? Okay, what about B? Okay, Mackenzie?
No, because it's not standard or normal distribution.
Oh, okay, thank you. Okay, when we can apply the central limit theorem, it will satisfy one of two, right? Okay, look at it here.
Oh, it's just one. It's not
Yeah.
both.
Okay, just one, because the central limit theorem say that one of two conditions. The first one is the sample size at least 30, right? The second one is the population is normal distributed. Okay, it just satisfies one of them.
Oh, okay. So then yes.
Yeah, yes, exactly. Because the sample size here is 50, right? So it satisfies the first condition. It not satisfy the first condition. It must be satisfy the second condition. Any questions so far? Okay, so that's we finished section 7.1, right? Any questions so far? Okay, this section is not difficult. Okay, you can look at my slide here. Ask me any question if you have. Okay, now we move on to the section 7.2. Okay, I will draw down a picture for this. Okay, we have a population and we have a sample. When we talk about a population like West State University, student at West State University, so we have a lot of sample, right? The sample 1, for example, the sample 2, the sample 3, the sample 3, and the sample 4, something like this. And for example, we will have the sample mean for this. X1 is the mean of this, and X2 is the mean of this, and X3 is the sample mean of this, and X4 is sample mean of this. And all the mean here we can, and the question here is, how do we calculate how to calculate the okay, how to okay, for example, we have the population in mu here, the mean here, mean of the population in mu here. And the question is I choose randomly one sample in this population, and I want the mean is, for example, and the mean here is 100. Okay. And I choose randomly one sample, and I want the sample mean will be greater than one specific number. Okay. For example, I want the sample mean is greater than 102, for example, like this. How to do that? How to calculate this probability? What is the chance of this? Okay, I choose randomly one sample, and I want to know what is the probability when I choose the sample have the sample mean is greater than 102, for example. Okay, for example, I consider the population is the student at West State University, and I want to measure the average GPA of student. And you know that for each sample here, is the class student in Pacific class, right? So they will have different GPA score, right? Okay. And now I will choose randomly one class, okay, one sample, and I want to choose one sample that the average GPA will be greater than 4, something, or greater than the GPA will be greater than. I want to choose a sample that the GPA will be greater than 3.0 over 4. For example, I want to choose one sample like this. Okay, the question here is, what is the probabilities of choosing this kind of sample? Right? Okay, how to do that? Okay, in this section, they will answer this question. Okay, how to calculate the probability of choosing a sample like this. Okay, clear, right? That's the introduction about this section. And the objective of this here is use the central limit theorem to find the probabilities of the sample means. Okay, find the probability of sample means. The question here is the probability of choosing this kind of sample. I want to choose the sample that the GPA is greater than this number. Okay. How to do that? Okay, that is the introduction. So now we move on to solve the problem. Okay. Okay, the first formula is the standard score for the sample mean. Okay, the sample mean. Okay. When they ask you to find the they ask you the sample mean, right? So we can use the formula in the previous course. Z here will be calculated by x bar minus mu over sigma. Right? Okay. Because here we consider the sample here. The sample is the x bar minus mu x bar over sigma x bar. Okay, because the central limit theorem say that the mu x bar here is equal to mu, right? Because the central limit theorem say that the means of the sampling distribution equal to the mean of population. So the mu x bar will be equal to mu. And the standard deviation of sampling distribution will be equal to sigma over square root of n. Okay. So in this case, we can use this formula to calculate the standard score of sample mean. Why we need to do that? Because when we know the standard score, we can use the table. We can use the table of the distribution, the normal distribution here, to find the probability. Okay. The first one we need to change the x score to the z score. Okay. That is the first one when we to do that. Okay. I will give you some example for this to practice. Okay. Let's see. Okay, so now I have. Okay, I will example here. Example. I will have the mu of the population is 35, and the standard deviation of the mean of the population is 9, and n here is 64, and the same. I choose a sample mean. I choose a sample, right? Sample of 55 size, right? And x bar here is the sample mean of this sample. X bar here is the sample mean. X bar here is 60, something like this. So the question is, what about the z-score? X bar. Okay, this is the first step when we want to calculate the probability of choosing the sample mean having the mean is 60. We need to change to the z-score. Okay, how to do that? Okay, so now I will apply this formula. Okay, I will apply this formula. Okay, this is x bar minus mu over sigma square root of n. Okay, what about x bar here? X bar here is 60, right? 60, right? Minus. Okay, what about mu in this case? Mu in this case 30. Oh no, sorry, I want to not much. It's maybe 40. Okay, it's just 40. And the mu here is the 35, right? And the sigma here is 9. And the n here is 64, so it's related. And after that, you will get the z-score for this. 9 over square root of this one. So it is 44. Okay. That's the first one. When we want to when we find about the z-score of x bar. Okay, that is the first step. Clear, right? Okay, that is just apply the formula for this. Okay. So now we will move on to the example. Okay. Before move on to the example, I will give you how to calculate the probability step by step. Okay. For example, I have the population level. X bar is the mean of this, mu is the mean of this, and deviation is sigma. Okay. And the sample here, and they have the x bar is the mean, okay, mean. And the question is to find probabilities of the sample mean is less than or equal specific value, x value, specific value. Okay. How do you do that? Step one, change x bar to z value. Change x bar to z value. That is the first one by using the formula in the previous slide. By this formula here, z is equal to x bar minus mu over sigma over square root of n. And step two. The probabilities of x bar is less than a specific value. Okay. will be less than, will be equal to, we approximately the probability of z less than z. Okay. And it's similar to probability of x bar greater than value is approximately probability of z greater than z. Okay. So to find the probability of x bar less than the value, we can find the probability of z less than z value. In this case, we calculate this one is better because what this can be found by using the table of normal distribution, right? We can use this table to find the probability of this, and after we can learn about this. Okay. So look at the example 7.4. Okay, look at the second 7.4. According to the standards of 40Z control and prevention, the mean total cholesterol level for a person 20 years of age and older in the United States was 197. Okay, could you tell me what about the mean of population in this case? What about the mean of population in this case? Madeline, okay.
It's 197.
Okay, exactly. Okay, the mu here is the, okay, you look at the keyword, the mean, right? The mean total cholesterol level, it was this number, right? Okay, we have the information for this. And the second, okay, look at the, okay, not the A, not the B. What is the probability that a random selected sample, okay, now I want to choose a random sample, and I want the mean here will be less than 183. Okay. So x bar here is 183, right? You look at the keyword here, the mean, right? The mean of the sample is less than or this number, right? Okay, x bar here, I want to choose this. Okay. And what about n here? What about the sample size in this case? You please.
150.
150. What's your name, please?
Shreya.
Zero. Okay, you to answer. Okay, 3. And here is 1. Okay, that's in the end, right? What about the standard deviation in this case? Tyler, right?
Yes, 35.
Okay, exactly. 35. Okay, so we list all the assumption here, right? Okay. The first one, we need to list all the assumption. Right. The step 1, change x bar to z value. Right? Change x bar to z value. Okay. We have this formula. Z equal x bar minus mu over this number. So x bar here is 183 minus mu here is 197, and over sigma here is 35 over square root of 150. So now you will get the value here. So the problem, the answer should be the negative 4.9, right? 4.9. Okay. Is it clear this time? Just change the x value to z value. Okay. And now we apply the step 2. Probability of choosing the sample is less than this number is approximately find the probability of z less than this number. Right? So using the table to find this. Right? If you cannot find this means okay, I will draw the picture for this. 0, right? This is -1, -2, -3. if you cannot find this because very small, right? Very small number. So it will be like this in this side, right? Okay. So the probability will be approximate 0. So now it will be 0, right? Because the area of this one is very small, right? The area of this one is very small, so it's 0. Right? Okay, so that means that we cannot find the sample when we calculate the probability is 0. That means that we cannot choose a sample like this. You cannot choose a sample having the mean less than 183. We cannot do that, right? Because the probability here is very close to 0. Okay. Clear, right? That's either the meaning of this. Okay, so I think I cannot cover all the content of this section today. We will talk about this in next question. So I will make the attendance for you now. Samia,
Here.
Hannah here, Laurel, Xavier, Kylie, Bobby, Christopher Dollar, Shaylee, Mackenzie here, Robbie here, Ben the Crossinger, okay, Abdul Hamid, Jonathan Peter, Kidman, Ruth here, Chen Liu here, Delaney here, Ordelia, not here, Alondra,
Yeah.
Matu,
Here.
where Matu? Okay, you, okay. Reed,
Here.
okay, here. Tyler, okay, here. Aliyah, Yasi not here, Sullivan not here, Maria here,
Here.
Thomas not here, Priya here,
Here.
Cameron Waller not here, Waller, Tyler, not here. Okay, thank you for your attention. Have a good day.
Thank you.
Thank you.
Have a good one.
Yeah, you too.